Jump to content. Main menu. Main menu, move to sidebar, hide. Navigation. Main page, help browse cookbook Wikijunitor feature books recent changes random book using Wikibooks. Community. Reading room forum community portal bulletin board help out. Policies and guidelines contact us. Search. Search. Appearance. Donations create account login. Personal tools. Donations create account login. Pages for Longbout editors learn more. Contributions discussion for this IP address. Contents move to sidebar hide. Beginning. 1. Introduction. 2. Fundamentals of active control of noise toggle fundamentals of active control of noise subsection 2.1 control of a monopole by another monopole. 2.2 Active control for waves propagation in ducts and enclosures. 2.2.1 Ducts. 2.2.2 Enclosures. 2.3 Active control and psychoacoustics. 3. Active control systems toggle active control systems subsection 3.1 Feed forward. 3.2 Feedback. 4. Applications toggle applications subsection 4.1 Noise cancelling headphone. 4.2 Active control for cars. 4.2.1 Motor noise. 4.2.2 Tires noise. 4.2.3 Aerodynamic noise. 4.3 Active control for aeronautics. 5. Further reading. Toggle the table of contents. Acoustics/active control. Add languages. Add links. Book discussion. English. Read edit source view history. Tools. Tools move to sidebar hide. Actions. Read edit source view history. General. What links here related changes upload file special pages permanent link page information site this page gets shortened URL download QR code. Sister projects. Wikipedia Wikiversity Wiktionary Wikiquote Wikisource Wikinews Wikipedia Commons Wikidata Media Wiki MetaWiki. Print/export. Create a collection download as PDF printable version. In other projects. Wikidata item. Appearance move to sidebar hide. From Wikibooks, open books for an open world. Acoustics. Introduction edit vertical line edit source. The principle of active control of noise is to create destructive interferences using a secondary source of noise. Thus, any noise can theoretically disappear. But as we will see in the following sections, only low-frequencies noises can be reduced for usual applications, since the amount of secondary sources required increases very quickly with frequency. Moreover, predictable noises are much easier to control than unpredictable ones. The reduction can reach up to 20 decibels for the best cases. But since good reduction can only be reached for low frequencies, the perception we have of the resulting sound is not necessarily as good as the theoretical reduction. This is due to psychoacoustics considerations, which will be discussed later on. Fundamentals of active control of noise edit vertical line edit source. Control of a monopole by another monopole edit vertical line edit source. Even for the free space propagation of an acoustic wave created by a punctual source, it is difficult to reduce noise in a large area, using active noise control, as we will see in the section. In the case of an acoustic wave created by a monopolar source, the Helmholtz equation becomes P plus K to P equals J0Q \displaystyle delta P plus K circumflex accent to P equals J \omega \rho underscore 0Q, where Q is the flow of the noise sources. The solution for this equation at any m point is ppm equals J0Q page for PE. JKRPR P \displaystyle P underscore PM equals frac J omega rho underscore 0Q underscore P for pi frac P circumflex accent JKR underscore PR underscore P, where the P mark refers to the primary source. Let us introduce a secondary source in order to perform active control of noise. The acoustic pressure at that same m point is now PM equals J0Q page for PE. JKRPR P plus J0QS for PE, JKRSRS \displaystyle RM. PM equals backslash frac backslash ORMJ backslash omega backslash road underscore backslash ORM0 Q underscore P4 backslash pi backslash frac E circumflex accent JKR underscore PR underscore P plus backslash frac backslash ORMJ backslash omega backslash road underscore backslash ORM0 Q underscore S4 backslash pi backslash frac E circumflex accent JKR underscore SR underscore S. It is now obvious that if we chose QS equals QPR SRPE JKRP RS backslash display style Q underscore S equals Q underscore P backslash frac R underscore SR underscore PE circumflex accent JKR underscore PR underscore S. There is no more noise at the endpoint. This is the most simple example of active control of noise. But it is also obvious that if the pressure is 0 in M, there is no reason why it should also be 0 at any other endpoint. This solution only allows to reduce noise in one very small area. However, it is possible to reduce noise in a larger area far from the source, as we will see in this section. In fact, the expression for acoustic pressure far from the primary source can be approximated by PM equals J0 for PE, JKRPR PQP plus QSE, JKD cos backslash display style PM equals backslash frac J backslash omega backslash road underscore 0 for backslash pi backslash frac E circumflex accent JKR underscore PR underscore PQ underscore P plus Q underscore SE circumflex accent JKD backslash cos backslash data control of a monopole by another monopole. As shown in the previous section, we can adjust the secondary source in order to get no noise in M. In that case, the acoustic pressure in any other endpoint of the space remains low if the primary and secondary sources are close enough. More precisely, it is possible to have a pressure close to 0 in the whole space if the endpoint is equally distant from the two sources and if d backslash lambda slash 6 where d is the distance between the primary and secondary sources. As we will see later on, it is easier to perform active control of noise with more than one source controlling the primary source, but it is of course much more expensive. A commonly admitted estimation of the number of secondary sources which are necessary to reduce noise in an R-radius sphere, at a frequency f is n equals 36 PR to f to c2 backslash display style n equals backslash frac 36 backslash pi r circumflex accent to f circumflex accent to c circumflex accent to. This means that if you want no noise in a 1 meter diameter sphere at a frequency below 340 Hz, you will need 30 secondary sources. This is the reason why active control of noise works better at low frequencies. Active control for waves propagation in ducts and enclosures. Edit vertical line. Edit source. This section requires from the reader to know the basis of modal propagation theory, which will not be explained in this article. Ducts. Edit vertical line. Edit source. For an infinite and straight duct with a constant section, the pressure in areas without sources can be written as an infinite sum of propagation modes, Px, y, z, equals n equals 1 and the nn, x, y, e, j, k and z backslash display style px y z backslash omega equals backslash sum backslash limits underscore n equals 1 circumflex accent and a underscore n backslash omega backslash phi underscore n x y e circumflex accent j k underscore n z where backslash display style backslash phi are the eigenfunctions of the Helmholtz equation and represent the amplitudes of the modes. The eigenfunctions can either be obtained analytically, for some specific shapes of the duct, or numerically. By putting pressure sensors in the duct and using the previous equation, we get a relation between the pressure matrix P pressure for the various frequencies and the A matrix of the amplitudes of the modes. Furthermore, for linear sources, there is a relation between the A matrix and the U matrix of the signal sent to the secondary sources. The S equals KU backslash display style A underscore S equals Q and hence, the E equals a P plus the S equals a P plus KU backslash display style A equals A underscore P plus A underscore S equals A underscore P plus Q. Our purpose is to get A equals 0, which means the P plus KU equals 0 backslash display style A underscore P plus Q equals 0. This is possible every time the rank of the K matrix is bigger than the number of the propagation modes in the duct. Thus, it is theoretically possible to have no noise in the duct in a very large area not too close from the primary sources if there are more secondary sources than propagation modes in the duct. Therefore, it is obvious that active noise control is more appropriate for low frequencies. In fact, the more the frequency is low, the less propagation modes there will be in the duct. Experiences show that it is in fact possible to reduce the noise from over 60 decibels. Enclosures. Edit vertical line. Edit source. The principle is rather similar to the one described above, except the resonance phenomenon has a major influence on acoustic pressure in the cavity. In fact, every mode that is not resonant in the considered frequency range can be neglected. In a cavity or enclosure, the number of these modes rise very quickly as frequency rises, so once again, low frequencies are more appropriate. Above the critical frequency, the acoustic field can be considered as diffuse. In that case, active control of noise is still possible, but it is theoretically much more complicated to set up. Active control and psychoacoustics. Edit vertical line. Edit source. As we have seen, it is possible to reduce noise with a finite number of secondary sources. Unfortunately, the perception of sound of our ears does not only depend on the acoustic pressure or the decibels. In fact, it sometimes happens that even though the number of decibels has been reduced, the perception that we have is not really better than without active control. Active control systems. Edit vertical line. Edit source. Since the noise that has to be reduced can't never be predicted exactly, the system for active control of noise requires an auto-adaptable algorithm. We have to consider two different ways of setting up the system for active control of noise depending on whether it is possible or not to detect the noise from the primary source before it reaches the secondary sources. If this is possible, a feed-forward technique will be used, aircraft engine for example. If not, a feedback technique will be preferred. Feed-forward. Edit vertical line. Edit source. In the case of a feed-forward, 2 sensors and 1 secondary source are required. The sensors measure the sound pressure at the primary source detector and at the place we want noise to be reduced control sensor. Furthermore, we should have an idea of what the noise from the primary source will become as he reaches the control sensor. Thus we approximately know what correction should be made before the sound wave reaches the control sensor forward. The control sensor will only correct an eventual or residual error. The feed-forward technique allows to reduce one specific noise, aircraft engine for example, without reducing every other sound conversations. The main issue for this technique is that the location of the primary source has to be known, and we have to be sure that this sound will be detected beforehand. Therefore, portative systems based on feed-forward are impossible since it would require having sensors all around the head. Feed-forward system. Feedback. Edit vertical line. Edit source. In that case, we do not exactly know where the sound comes from, hence there is only one sensor. The sensor and the secondary source are very close from each other and the correction is done in real time. As soon as the sensor gets the information, the signal is treated by a filter which sends the corrected signal to the secondary source. The main issue with feedback is that every noise is reduced and it is even theoretically impossible to have a standard conversation. Feedback system. Applications. Edit vertical line. Edit source. Noise cancelling headphone. Edit vertical line. Edit source. Usual headphones become useless when the frequency gets too low. As we have just seen, active noise cancelling headphones require the feedback technique since the primary sources can be located all around the head. This active control of noise is not really efficient at high frequencies since it is limited by the Larsen effect. Noise can be reduced up to 30 decibels at a frequency range between 30 Hz and 500 Hz. Active control for cars. Edit vertical line. Edit source. Noise reduction inside cars can have a significant impact on the comfort of the driver. There are 3 major sources of noise in a car: the motor, the contact of tires on the road, and the aerodynamic noise created by the airflow around the car. In this section, active control for each of those sources will be briefly discussed. Motor noise. Edit vertical line. Edit source. This noise is rather predictable since it is a consequence of the rotation of the pistons in the motor. Its frequency is not exactly the motor's rotational speed though. However, the frequency of this noise is in between 20 Hz and 200 Hz, which means that an active control is theoretically possible. The following pictures show the result of an active control, both for low and high regime. Low regime. Even though these results show the significant reduction of the acoustic pressure, the perception inside the car is not really better with this active control system, mainly for psychoacoustics reasons which were mentioned above. Moreover, such a system is rather expensive and thus are not used in commercial cars. Tires noise. Edit vertical line. Edit source. This noise is created by the contact between the tires and the road. It is a broadband noise which is rather unpredictable since the mechanisms are very complex. For example, the different types of roads can have a significant impact on the resulting noise. Furthermore, there is a cavity around the tires, which generate a resonance phenomenon. The first frequency is usually around 200 Hz. Considering the multiple causes for that noise and its unpredictability, even low frequencies become hard to reduce. But since this noise is broadband, reducing low frequencies is not enough to reduce the overall noise. In fact, an active control system would mainly be useful in the case of an unfortunate amplification of a specific mode. Aerodynamic noise edit vertical line edit source. This noise is a consequence of the interaction between the airflow around the car and the different appendixes such as the rear views for example. Once again, it is an unpredictable broadband noise, which makes it difficult to reduce with an active control system. However, this solution can become interesting in the case an annoying predictable resonance would appear. Active control for aeronautics edit vertical line edit source. The noise of aircraft propellers is highly predictable since the frequency is quite exactly the rotational frequency multiplied by the number of blades. Usually this frequency is around some hundreds of hertz. Hence, an active control system using the feed-forward technique provides very satisfying noise reductions. The main issues are the cost and the weight of such a system. The fan noise on aircraft engines can be reduced in the same manner. Flow-induced oscillations of a Helmholtz resonator rotor-stator interactions. Flow-induced oscillations of a Helmholtz resonator acoustics rotor-stator interactions. Further reading edit vertical line edit source. Wikipedia has more about this subject. Active noise control. Active noise control at Dirac Delta. Retrieved from https://wikibooks.org/w/index.php title equals acoustics/active_control and bolded equals 3,263,646. Category Book: Acoustics. This page was last edited on August 12, 2017, at 3:50. Text is available under the Creative Commons Attribution Share Alike license. Additional terms may apply. By using this site, you agree to the terms of use and privacy policy. Privacy policy about Wikibooks disclaimers code of conduct developers statistics cookie statement mobile view